Okay, let's see if we can demystify probability just a little bit. This won't be an in-depth treatment of probability, of course, because there's entire graduate level courses dedicated to that topic in graduate schools for statistics. So this will just barely brush the surface. But the assumption here is that you really have very little idea about probability and what that is and how it fits into statistics. So that's where we're starting with this video. If you're beyond that, this video is probably going to be pretty boring to you. Alright, let's see if I can advance this slide a little bit here. There we go. Okay, so probability is one of those things that most people have some intuition about, but often our intuition is wrong. And here I'll just go over the highlights, concepts that are going to be useful later on because we're about to introduce hypothesis testing. But probability really is at the core of statistics. Concepts like average and expected value and even correlation, all of those things really rely on the concept of probability. So it's important that we understand what a probability is. Alright, so we do need a little terminology. I know learning new terminology is always very confusing and difficult. When I taught statistics, I used to tell students it's really not a math class, it's really a language class. Alright, so some terminology. An experiment is any act that produces an observable outcome. And some examples we use in order to introduce concepts are things like flipping a coin, rolling a die, selecting a card from a deck. But it also includes things like giving a person an experimental drug to see if it cures cancer. Flipping a coin is a simple experiment. Giving a person a drug to see if it cures cancer, that's a very complex experiment. But they are both acts that produce observable outcomes. So when we have anything that produces an observable outcome in probability theory, we're going to call that an experiment. The sample space of an experiment is the set of all possible outcomes of that experiment. And we usually use the symbol capital letter S to symbolize the sample space. So for the very simple experiment of flipping a coin, the sample space only has two things in it. Right? Heads and tails. Those are the only two outcomes of flipping a coin. Now, we can denote subsets of S with other letters, like A or B, X or Y, any letters we want. I'll typically use A and B to refer to two subsets of a sample space S. So, for example, the outcome heads from the experiment of flipping a coin is a subset of the sample space S for coin flipping. Alright, so given those terms, we are already ready to define probability. So the probability of an event A is just the total number of events that we could classify as A, so the total number of events in the set A, divided by the total number of events in the sample space S. That's what the probability is. So it's a proportion, it's a ratio. And from that definition, one thing leaps out at us. It can never be bigger than 1, and it can never be smaller than 0, because the smallest number of events that we could classify as A would be 0 events, and the biggest number of events that we could classify as A would be the same number of events that are in S. So in that case, you would just have the same... Oh, where's my laser pointer? That went off. There we go. You would just have the same number for A as S in the biggest case. So the smallest it could be is 0 if A is 0, and the biggest it could ever be is 1 if A is equal to S. A can never exceed S, right? Because S, by definition, is the total number of things that could possibly happen in the experiment. Okay. So then there are some axioms of probability. These are things that, in mathematics, an axiom is something that you don't prove, you take as an assumption. The first axiom of probability is that the probability of some event happening if we do the experiment is 1. And so if we're going to do the experiment, like if we're going to flip the coin, something's going to happen. It's either going to land on the heads face up or the tails face up. One of those two events is going to happen. So the probability of something happening is 1. And then we have something called the addition rule, which is that the probability of A or B is just going to be the probability of A happening plus the probability of B happening minus the probability that both A and B happen. Now, why do we have to subtract out the probability of A and B both happening? Well, we have to do that because otherwise we would be counting the probability of both happening in this probability and in this probability. So the probability of A and B is also included here in this term, the probability of A, and it's also included here in the term, the probability of B. So it would be included twice in this probability, and we would overestimate or overcalculate the probability of A or B happening if we just use this. So we have to subtract out the probability of both A and B one time happening. And the multiplication rule, the probability of A and B both happening, which is just this probability right here, is just the probability of A, the event A happening, times the probability that B happens, and then this up and down bar here means given, so the probability of B given that A happened. So the assumption here is that A happened, and then what's the probability of B if A already happened? That's going to be the probability of both A and B. Now, we do have a special situation where A and B, the two events A and B, are independent of each other. And in that case, the addition rule and the multiplication rule both simplify. I should say independent and mutually exclusive, meaning you can't have both. In that case, the addition rule simplifies to just the probability of A plus the probability of B. And then the multiplication rule simplifies to just the probability of A and B is just the probability of A times the probability of B. So we don't have to worry about this B given A. This, by the way, I should mention, is called a, well, this is, let's start with this one. Something like the probability of A or the probability of B, those are called simple probabilities. And this one here is called a conditional probability. So the probability that something happens conditioned on or given that something else happened. That's a conditional probability. All right. So let's do a couple of examples to make this more concrete, and we're just going to use coin flipping because that's a really simple model. It's something that most people have done at least once or twice in their lives, and most people have some intuition about coin flips and how they work. All right, so what is the probability of getting heads? I know you already know this. It's so obvious, right? Everybody knows it's 0.5 or 50%. But let's do it with the definition of probability so that you can understand how the definition works. And we'll do more complicated examples down the road. But let's just remind ourselves really quickly of what the definition of probability is. Here's the definition of probability again. It's just the number of events in the set A divided by the total number of events in the sample space S. So, can we use that to come up with this 0.5? We know the number is going to be 0.5, but how do we do that with the definition of probability? Well, we know that there's just two possible outcomes, right? So there's only two things in the sample space for flipping a coin, and that's one is heads and the other is tails. And then how many of those are classifiable as heads? Well, only one of them, right? So that gives us the one event that's classifiable as heads divided by the two total events in the sample space, and that gives us our probability of heads as being 0.5. All right, what's the probability of getting heads or tails? Well, that's just going to be the addition rule, right? So that's going to be the probability of heads, which we know is 0.5. What's the probability of getting tails? Well, there's only one event, just like with heads. There's one event classifiable as tails, two total events in the sample space, so it's also 0.5, right? So there's our addition rule. And so 0.5, the probability of getting heads, 0.5, the probability of getting tails. Then what's the probability of getting heads and tails on one flip of a coin? Well, you know coins, right? You can't get both heads and tails on one flip of a coin, so that's just 0. And so that then gives us our probability. You can see that that's going to add to 1. which is a good thing since those are the only two possible outcomes in that sample space, and we know again from the first axiom of probability that the probability of something happening in the sample space, the probability of S, has to equal 1. And this is also an example of two events that are independent and mutually exclusive, so our addition rule simplified down to the probability of A plus the probability of B. We really didn't need to worry about that probability of A and B. All right. So now, to illustrate the multiplication rule, we need to change the experiment a little bit. We need to complicate it just a little bit. What if we flip a coin twice instead of once? So that's a different experiment. What's the probability of getting heads on both flips of the coin if we're flipping this coin twice now? Well, remember our multiplication rule is just the probability of A times the probability of B. So it's going to be the probability, A in this case is the probability of getting heads on the first flip of the coin. B is the probability of getting heads on the second flip of the coin. And we know that both of those are 0.5. So the probability of getting heads on both flips of the coin is just 0.5 times 0.5, which is 0.25. Take out a hand calculator and verify that for yourself if you want. All right. So probabilities have some useful properties that help us to interpret them. One property is that, as I mentioned earlier, they can only range between 0 and 1. So the lowest a probability can ever be is 0, the highest a probability can ever be is 1, and that really helps us to interpret a probability. If I tell you the probability is 0.1 that something's going to happen, well, that's really close to 0, so that event is probably not going to happen, right? That event has a very low probability. So if I tell you there's a probability of 0.1 that it's going to rain today, you probably don't need to take your umbrella, assuming that that probability is accurate. On the other hand, if the probability is 0.9 that a certain event is going to happen, so if I tell you there's a probability of 0.9 or 90% chance of rain today, you should probably take your umbrella because it's most likely going to rain, right? On the other hand, if the probability is 0.5, 0.5 is about as uncertain as we can get about an event. At 0.5, we have no idea if that event is going to happen or not happen. We just have no information about it at all. Okay, so yeah, 0 means the event is certain not to occur. 1 means the event is absolutely certain to occur. And then the further we get from either of those ends, the less certain we are about the event. And then the last thing is the probability that something happens in an experiment has to equal 1, and this becomes very useful in hypothesis testing when we split the sample space up into two sets. Those two probabilities in the sample space have to add to 1, so that's going to be useful for us later on. All right, now let's do a slightly more complicated example to kind of set the stage for hypothesis testing. Remember our old friend, the normal distribution. Here it is again. What if I were to take a random sample of a single member of this population? So if this is a population of people and we've measured something about those people, like maybe their height, how tall they are, and then of course we must have done the z-transform since a normal distribution, these are z-scores. Actually, that's not true. That's only true for the standardized normal distribution. Normal distributions can have any number here on the x-axis, but these look like z-scores to me, so let's treat them as z-scores, and let's say we standardized people's height. We get a nice normal distribution, and we are going to take a random sample of just one person from this population. What is the probability that I would get a member who has a value of exactly 1? Well, it turns out that this probability is 0. Actually, I think it's technically undefined. That's because probability is actually the area under the curve, and there is no area under a single point in a continuous distribution. But we can ask the question, what is the probability of getting a value as big as 1 or bigger? So if I were to take a random sample from this population, what's the probability that I'm going to get a value at least as big as 1 or bigger, anywhere under this part of the curve right here. Okay? So that would be just the area under the curve to the right of 1. We can find that value in a normal distribution table. And so here's just a little tiny piece of a normal distribution table. And you can see what the information we get here in a normal distribution table. First we get the z-score. So that is the number of on the x-axis. So we can look up any number we want on this table. And then given that we have that number, we can get the area between the mean and z. So the mean here in this distribution that I'm showing you is 0. So I could get the proportion that's between the mean and a given z-score. So the area under this part of the curve right here. And I can get the area beyond z. So that's the area under this part of the distribution, this tail of the distribution. So we need to look up the number 1 in the z-table. Here it is. There's the number 1 right there. And then the area beyond 1 is right here. So we can see that it is 0.1587, or about 15.87%, or about 16%. If we were rounding to the nearest whole percent, about 16%. And what that means is 16% of the normal distribution curve is beyond 1 standard deviation from the mean. What about below 1? What's the probability of getting a score less than 1? Well, once we know the probability of getting a score bigger than 1, we can just use the first axiom of probability, right? Remember that the probability of S, the probability of something happening in this experiment, is 1. So if we know that the probability of getting something bigger than 1 is 0.1857, there we go, then we can just take that 0.1587 and subtract it from 1 and come up with the complement, which is 0.8413. So that would be the probability of getting something smaller than 1. Now we can also do it another way. We could do it another way by looking up the probability of getting something between the mean and the z-score that I'm looking at. So that's the probability of getting something between here and here. And then we can see that's 0.3413 for the z-score of 1. And I can just add to that then, because I know that the normal distribution, remember, is symmetric about the mean. So it's symmetric about this middle point here. And what that means is exactly half of the curve lies above the mean and half of the curve lies below the mean. So if I want to know what's the total proportion below 1, that's going to be this proportion here between 1 and the mean plus 0.5. And you can see if you add 0.5 to 3413, you do indeed get the same answer that we got by subtracting 0.1587 from 1, 0.8413. Yeah. Okay, what about the probability of getting a score at least as close to the mean as 1 or closer? Or in other words, getting a score within 1 standard deviation of the mean. So within a standard deviation, that means no further than 1 standard deviation above or below the mean. How could we figure that out? Well, going back to our table, this gives us the proportion that is between the mean and 1 standard deviation above the mean. And by symmetry, right, we know that the normal distribution is symmetric about the mean. We know that this also has to be the proportion between the mean and 1 standard deviation below the mean. So if I just take 2 of these, either multiply it by 2 or add this number twice, I will get the proportion, by the addition rule, I will get the proportion that lies within 1 standard deviation of the mean. And you can see there that that is 0.6826. Now you can do the same. I'm using 1 because it's a very convenient number, but you can do the same for any z-score at all. So no matter what score your observation takes, you can figure out the probability of getting a score at least that big, within the same standard deviations from the mean, or even further from the mean than the one you got. All right. Well, that's enough for now. Probability is the foundation for lots and lots of things in statistics. In fact, pretty much everything in statistics is founded on the concept of probability and probability theory. Likelihood, expected value, and even correlation are really all about probability. But that will give you hopefully that was a gentle introduction, and we'll take it up in the next video.